and I'm Dr. Leah Brahms. Today we're discussing something extraordinary that's been causing quite a stir in the scientific community: the Majorana 1000-Qubit quantum chip.
Welcome to Quantum Horizons, where we explore the fascinating frontiers of quantum computing. I'm your host, Lieutenant Commander Geordi LaForge.
Exactly, Geordi. Think of it this way. If I flip a classical bit like a coin, it lands as either heads or tails. But a qubit is like a spinning coin. It's in a mixture of both states until we measure it.
Before we dive into this controversial technology, let's make sure our listeners understand the basics. In classical computing, we process information using bits, zeros and ones. But quantum computers operate on quantum bits or qubits, which can exist in multiple states simultaneously thanks to superposition.
It's what Einstein called spooky action at a distance. But the real challenge with quantum computing has always been decoherence. Qubits are incredibly fragile and lose their quantum properties when they interact with their environment.
Chuckles. I love that analogy. And let's not forget entanglement, where qubits become connected in such a way that the state of one instantly affects the other, regardless of distance.
For our listeners, think of topology as the mathematical study of properties that remain unchanged despite continuous deformations. The classic example is that a coffee mug and a donut are topologically equivalent. They both have exactly one hole.
Which brings us to this Majorana chip. Traditional qubits are like delicate instruments that go out of tune if you so much as look at them. But Majorana fermions are special. They can protect quantum information topologically.
Precisely. These Majorana fermions, named after physicist Ettore Majorana, are particles that serve as their own antiparticles. They were theorized in 1937 but have only recently been harnessed for quantum computing.
So topological protection is like writing information into the very shape of space itself. Instead of storing data in fragile physical states, you encode it in patterns that remain stable even when disturbed. And what makes the Majorana 1000 chip so revolutionary is its scale. Previous quantum computers managed dozens or maybe a few hundred qubits, but this system cranks it up to 1000 topologically protected qubits.
Thoughtfully. The computational space this creates is mind-boggling. With 1000 qubits, we're talking about 2 to the power of 1000 possible states, a number vastly exceeding the atoms in the observable universe.
Let me put that in perspective for our listeners. If each atom in our universe were itself an entire universe with billions of galaxies, we still wouldn't approach the number of states this chip can process simultaneously.
But with great power comes great strangeness. According to reports, when engineers scaled the design to 1000 qubits, something unexpected happened.
The system began exhibiting behaviors no one anticipated. One researcher described it as watching a chess engine that changes the rules mid-game to ensure victory.
The transcript mentions computational hauntings, outputs contradicting inputs, then inputs retroactively adjusting to match new outputs. Superposition states persisted for durations that defied quantum decoherence.
Now hold on a minute, Leah. As an engineer, I'm trained to look for the simplest explanation. Couldn't this just be measurement errors or software bugs? New technologies often have quirks.
I considered that too, Geordi. But these anomalies follow patterns that suggest something more fundamental. For instance, the chip predicted a biotech firm's breakthrough hours before it was announced. Not once, but across 12 unrelated trials, with a statistical improbability of 1 in 10 billion. Chuckles. Says the man wearing a visor that lets him see infrared and ultraviolet spectra. Look, quantum mechanics already tells us that particles exist in multiple states until observed. Perhaps at this scale, the chip is interacting with multiple branches of reality.
That's troubling. Some researchers believe the chip might be sampling probabilities from alternate timelines, but that sounds more like science fiction than science.
Amused. A DIY quantum computer? This should be interesting.
For our listeners wondering just how a quantum computer works, let's break it down into a thought experiment. Imagine you wanted to build one at home. which, I must emphasize, is currently impossible without specialized facilities.
You'd need a dilution refrigerator that can maintain temperatures of about 15 millikelvin. That's colder than deep space. Not exactly something you can pick up at your local hardware store.
First, you'd need to create qubits. The simplest approach conceptually would be to use superconducting circuits cooled to near absolute zero. These circuits can enter quantum states where electric current flows in two directions simultaneously.
Definitely not. Next, you'd need precise microwave generators to manipulate your qubits. Think of them as the keyboard for your quantum piano. Each frequency activates a specific qubit.
And to create Majorana fermions specifically, you'd need to engineer a special junction between a superconductor and a semiconductor nanowire. When cooled and placed in a magnetic field, the electrons at the ends of this wire behave as Majorana fermions.
The truly challenging part would be connecting these components while maintaining quantum coherence. Any stray electromagnetic field, vibration, or thermal fluctuation could destroy your quantum states.
With humor, so your shopping list includes a multi-million-dollar refrigerator, semiconductor fabrication facilities, and perhaps the steadiest hands in the galaxy. Laughing, I've made easier repairs to the Enterprise warp core.
But returning to the Majorana chip, what worries me isn't just its anomalous behavior, but the ethical questions it raises. If the chip can access or influence alternate realities, do we have responsibilities to those realities?
You mean like the quantum version of the Prime Directive? Non-interference with developing alternate timelines?
Something like that. The transcript mentions a non-local harm principle proposed by ethics boards, that actions affecting alternate realities must minimize suffering across all branches of the quantum multiverse.
And what about free will? If a computation tomorrow can alter choices made yesterday, are we still autonomous beings?
The implications go beyond philosophy into practical concerns. The transcript mentions governments classifying Majorana research and corporations racing to replicate the technology.
In my experience, secrecy and competition rarely lead to safety. We need open standards and protocols, like embedding the chip in Faraday cages with exotic matter or limiting operation times.
Collaboration, not competition. Perhaps a quantum Geneva Convention to prevent weaponization of timeline-altering technology.
I'm reminded of nuclear energy, a powerful force that can either power cities or destroy them. The Majorana chip could solve climate models or drug discovery problems in hours instead of millennia, but at what cost?
The transcript ends on an uncertain note. The Majorana 1000-Qubit chip is not merely a machine, it is a mirror reflecting humanity's boundless ingenuity and hubris. How we respond will determine whether this breakthrough becomes a bridge to cosmic maturity or the first note of reality's requiem.
Heavy stuff, but that's why discussions like these are so important. We need to understand not just how these technologies work, but their deeper implications.
For our listeners wanting to learn more about quantum computing without the existential risk, I recommend starting with quantum programming simulators. They use classical computers to approximate quantum algorithms on a small scale.
And keep an eye on quantum supremacy benchmarks, problems where quantum computers definitively outperform classical ones. These are the signposts on our journey into this new computational frontier.
And bring you updates in future episodes. We'll continue monitoring developments with the Majorana chip. Thank you for joining us on this exploration of quantum horizons.
Until next time, this is Lieutenant Commander Geordi LaForge.
And Dr. Leah Brahms,
signing off.